Hello guys, with me again. This is Control Engineering Chapter 2. Now we are looking at the mathematical modeling. As basically you may have seen in Lecture 1, um, mathematical modeling is part of the design process in any control system. Okay, so in this very chapter, we will be looking into building and constructing mathematical model of different control system, and from that mathematical model we will be constructing a block diagram. And then once we construct a block diagram, we will see how we can use some rules to manipulate the block diagram to simplify the block diagram so that we can simplify our mathematical model. And then we are going to use a tool called signal flow graph to do this simplification. All right. As an introduction, basically this slide goes back to lecture 1. They say here the first step in analysis and design of any control system is basically to get the system specification. And next, we have to draw the block diagram, and then this schematic or diagram of subsystem. And then we are going to construct the mathematical model, and then you can basically prototype the thing. All right. For this mathematical modeling, we have basically, you have to understand and know the basic mathematical concept of any control system. Okay. Here they say a system represented by a differential equation is difficult to model as a block diagram, and then Laplace transform is being used. Got the system transfer function with all initial condition are set to 0. Okay, so we can use basically the differential equation. We can construct many and complex and long formulation or mathematical model using the differential equation, but the problem is that the mathematical model or the equation will becoming complex and very long. So to simplify this, basically we normally use Laplace transform so that we can see a shorter version of mathematical model, and it's easier to work with a shorter formula rather than the long formula. Okay, so in this case we use Laplace transform to simplify this long differential equation of mathematical model of any control system. Okay, so you have to more or less familiarize yourself with this table, because this is Laplace transform. As you can see on the left hand side, everything works on t. This is on the time domain. When you look at the middle column, basically you are looking at the Laplace transform version of the time domain formula, and of course they have the name on the right hand side. So basically when you have to get familiarized with this thing, given the time domain, what is the Laplace version of it, given the Laplace version, what's the time domain of it. So you have to be very good in using these two terms interchangeably. All right. So the concept of transfer function has been basically revealed in the previous chapter. Okay, it says here it can be obtained by transforming the differential equation in the time domain into Laplace domain. So, for example, here you have the transfer function. Okay, basically in the time domain, because you have the t term down there. So what you can do is you can use the Laplace rules here, the interchange of between the time domain to the Laplace domain. You can use it here, and you will finally get this s squared plus 4s plus 3 divided by s cubed plus 3s squared plus 7s plus 5. So you try to basically work on this, converting from the time domain differential equation to the Laplace domain. You can basically try yourself. So basically, in the control system, we are formulating a mathematical model for different kind of problem, different kind of application. All right, for this particular topic, we will see how do we come out with mathematical model. For instance, here they say when we work with electrical or electronic circuits, we have to come up with a mathematical model of the circuits. So when we are working with translational, rotational gear system, hydraulic, liquid level, and thermal, we have to deal with different kind of items, different kind of elements in the specific control system, and we have to basically describe the function of this element in the mathematical equation. For example, if we work with electrical here, we are working with capacitors, resistors, and inductors. Right. This is the basic elements in the electrical system. So when we saw circuit, something like this, so basically we know what kind of mathematical model that we need to come up with. All right. So for this particular system, when we work with, for example, capacitor, when we need to output in terms of voltage, all right, in the function of current, so we can use this example here, Vt equal to 1 over C integral of I over tau and d over tau, I tau d tau down there. All right, so this is how you pick up this formula depending on what term that you are working and what are the input term and what are the output term. In this case, voltage is the output, current is the input. If you go next, the same for the capacitor, you can have output current and voltage as the input, and so on. So this basically this basic concept you can use for the resistor and for the inductor as well. Okay. Okay, this is nothing. For example, here in the very basic circuit, you have the Vt as a voltage supply, and you have the It as the current in the loop. You have three elements in this circuit. You have inductor, resistor, and capacitor. And of course, you have to understand the voltage current law. You can use the Kirchhoff law and everything, which says that the amount of voltage that consume or drop in all the elements in the circuit is equal to the supply voltage Vt. So Vt is equal to the summation of voltage drop in inductor plus the resistor plus the capacitor, and you will have everything will be summed up and equal to the supply voltage Vt. So you can basically first rearrange the formula. You can have the voltage drop in the inductor, so you have to go back to the, now we are working with the voltage in the right hand side, and on the left hand side is basically current, because we are describing voltage equal to voltage in the supply equal to voltage that drop in each of the components or element. So on the right hand side you have voltage, on the left hand side you have to know that V is equal to IR. So basically R is your impedance, I is the current. Okay, so impedance for each of these elements is given here, 1 over C, R, L, and also LS. So basically you have 1 over C and the R term and also L term. All right, then you have the current term. So to get because from this table 2.3 you have all these three elements. You can pick different formula for different application. In this case, we want to have voltage and the output and current in the input. So we are talking about relation between V and I. So we have to find here V and I voltage and current. We want to have V in the output and I in the input. So we may want to select the first column of relationship between voltage and current. For the capacitor, you will take 1 over C integral of I tau in d tau. For the capacitor, you will take just R I t. For the inductor, will take L di dt. All right. So we transfer all these things, all this trading into the formula, and from there you can simplify and use Laplace transform. This is how you get Vs is the voltage output of the Laplace transform, and Vcs is the voltage input in the Laplace transform. And of course, from there you can get the whole system mathematical model is by Vs over Vc. All right, so this is basically how you simplify the whole thing and forming up a mathematical model. Okay, so the same thing here, you have to basically know how to use the circuit analysis tools. All right, this is example for one loop system, this is multiple loop, and this is how you sum up everything. So the basic thing here is the circuit analysis method. Then you can basically construct the relationship between input and output terms that you put into the formula, and from there, just pick up the term from the table and do the replacement, convert to Laplace transform, and you will have the input over output transfer function. All right, the next one is basically modeling control system that use translational element. For example, here we have spring, we have mass, and we have damper. Okay. Previously, we are working with electrical systems. We work with capacitor, inductor, and resistor. Okay, but now we are looking at the pure mechanical things, which is the translational system. But here we will work with different elements, which are the spring, the mass, and the damper. Okay. Okay. So also the same with the electrical system. We will basically have the very same formulation as the one you may have seen in the electrical system. For example, here for the spring, you have xt, the displacement, and you have the k, the spring constant, and the ft, the movement of force over there. So the force, basically, you can the force and the displacement can be formed into different terms and different formula. For example, if you need force and velocity, you can use the first term. If you need force displacement, you can use the second term. The same for damper and also mass. So you have options here to use the formula of force velocity or force displacement. All right, depending on the kind of analysis that you do in any control system, you have to select the most suitable one. Okay, so also you have impedance for the whole thing. Okay, so more or less the same thing as electrical system. You have impedance representation at the last part. Okay, so in the system of electrical, we are working with Kirchhoff current law or something. But in the mechanical system, basically, we require the one differential equation called equation of motion, right? Because this translational, rotational, and many others, basically they are involving movement and motion. Okay, so to be able to do this, we have to know how to use the free body diagram and Newton law to form the differential equation. Then from there, we can when we have the formula, we use the Laplace transform from the table to get the transfer function. Here, for example, find the transfer function of we have mass, spring, and damper. That's the free body diagram. Once you have the free body diagram, you can basically come up with the system transfer function. Okay, You just have to rearrange the free body diagram so that it is correctly drawn. Look at the value and the direction, and from there, from that, you can basically put it into the equation of motion formula and Newton's law, and from there you can pick up the term from the table, do the Laplace transformation, and you will get the transfer function at the end of the day. So this is xs over fs. So you have to find the xs function in term of fs. So xs is basically the displacement, fs is the force. So if you look at this table, you have to go for force, displacement, column number 1, 2, 3, column number 3. So these are the terms that you have to pick up, not the force velocity. Unless if you are working with the force velocity, that maybe that's the right one to do. Okay. So looking at each of the element, the same as we look at the resistor, the inductor, and the capacitor, we can do the same thing with the mechanical system. For example, here the spring. So you know K is the spring constant, the stiffness. Xt is the displacement. So the relationship between the X, the K, and the F is given in the formula. Okay, so when you are working with this is only one X, one displacement. In this example, you have two displacement, and the formula goes like that. And basically, this is the block diagram of one spring system with two displacement. So if you happen to work with any block diagram that has basically one spring with two displacement, this is the block diagram of the system. You have x1t the input, x2t also as the input of the system, because you have two displacement, x1 and x2, and then the difference between this x1 and x2 is becoming the input to the k. Okay, you can relate back this thing to the formula here. F of t is equal to k, in which you have x1 minus x2. So the same thing here, x1 minus x2 multiplied by k, you will have the fx. So this block diagram, you can basically simplify and get the formula of this one. Okay. This is something a bit more complex, but you just have to follow the basic rule of any control system that use translational motion. You must have the right free body diagram. Then from there you have to sort out the formula. In this case, you have F equal to ma, so m is the a. You have to take force and here, force and velocity. Okay, from this table you have to work with force and velocity because your equation is involving some kind of velocity. Okay, so for the mass, find the velocity for the mass. So basically you will have the final formula just like that. All right, so this is the block diagram of mass. You have output, displacement is the output, input is the force, and you have the transfer function of mass system. This one you have mass and spring, and you can see there are two formula involved in this setup. You have displacement of spring. You have x0 and x1, and you have k down there. In between, you have the function of velocity, the function of what they call that force in terms of the mass. All right. So for this very basic system, you can combine basically the spring block diagram and the mass block diagram to become this block diagram. Okay, so this is the damper. The damper will take this kind of block diagram. The X in the input and force in the output, and CD is basically the term set between the block. Okay, so you have here x1, you have X and you have F. All right. So you have two formula involved. The spring and the damper is very well connected, and finally this is what you have for the spring and damper system. This is the very basic block diagram for spring and damper. Okay, now we are looking at mass, spring and damper, in which you have three elements together in one system. So you have the spring force, you have the force on the mass, and as well as the damper force. So you have all these three formula. Then you combine all these three. Basically, you can try yourself. You will finally have to construct something like this, that is having three elements of mass, spring, and damper. So you can sort this thing out yourself. All right. This is modeling of rotational system. Also similar with translational, similar with electrical. You also have three elements, right? With which is the shaft stiffness, fluid friction, and mass movement of inertia J. You have K, B, and J. Previously, you have MD and C. All right, and of course, this is the variable that you are working with, the angular displacement. Theta, you have angular velocity. Omega, you have angular acceleration. Alpha and torque. Okay, these are the parameters that involve in this thing. So if the whole system, combined together, you have to work with all of these things in one system. So if you have some kind of damper, you are working with the rotational damper. If you have the K, that something which looks like a spring, that you have to work with rotational stiffness. And if you have mass, you are working with the inertia. And these are the terms basically that you have to use in order to describe the rotational mechanical system. It's the same as translational. It just use different terms. You still have mass, you still have element of spring, you still have element of damper. And when you have all these three things, your block diagram will be looking like this. You can try yourself. Again, this one also the same, except for this is for the rotational system with the torque, with the gears. All right, so you have torque, you have angular acceleration, you have angular velocity, and you have angular displacement. Okay, and of course you know the gear ratio calculation, and also we also have mathematical model for hydraulic system. Okay, this is very typical hydraulic system. You will have spool displacement xt, you have piston displacement yt, and the volumetric flow rate qt. Also, these three elements basically represent the same parameters as the rotational and translational and maybe electrical. You always have three elements that represent some mass, element that represent the spring, and element that represent the friction of damping. Right, just take a different term, and if you are working with a system, control system that use hydraulic system, you basically work on these three elements and just use the terms that basically describe the hydraulic system here. Okay, so this is the very basic one. You can see how hydraulic system is being modeled and its own block diagram. And the same, I think, goes to liquid level system, where you have the level of H of T, and you have the flow rate of Q of T, and the parameters is pipe resistance and tank capacitance C. So we are still working and going back and forth with the same terms here. All right, so you have HT and QT. HT is the height of the tank, QT is the flow rate. So the resistance here is taking HT over the flow rate, and of course the whole liquid level system is working using the principle of mass conservation. Fluid into the tank is equal to rate of increase of HT plus the outflow. Okay, so you can basically take everything, replace into the system. Basically, you will have the Laplace term, and you can basically draw a block diagram of the system. You can work from this formula, and you can try to construct block diagram yourself. All right. So this is a thermal system, I think I'm not going to go through because this one won't be asked in the exam. All right, so for this block diagram manipulation method, I think here we work on the simplification of block diagram to see if the block is in series, parallel, how to go about with the mathematical model. So if you have block in series, you have to just add the formula. If the block is in parallel, you have to, you know, what they call that. You add with 1/over of that transfer function of the block. You know, this is very easy. I don't have a diagram in this slide. Sorry. So this is the next one here is the signal flow graph. Signal flow graph is the concept of how we play around with the subsystem of any I would say control system, which is the signal lines. All right. This is the concept. If you have x1t the input and x2t the output, basically you can basically create node or create branching for this kind of block diagram. For example, if you have 2t, if you have two signal flow graph joining at 1t, so here you have the formula yt is equal to mx of t plus 1 multiplied by the c of t. So this is basically if you have signal coming in and joining at y, this is y is going to take the term, the new term of addition of between these two line, in which you have to multiply the branch there or the process with the input. All right. So this is on the different case. Yt here is 3xt and zt is minus 4 times xt. I think this is quite clear. This is product. Okay. This is Mason gain formula. Also, is a tool for you to be used to simplify the block diagram. All right. You can use Mason gain formula basically to simplify the block diagram by this kind of block diagram. You can break down everything into this formula, and from there you can use the Mason gain to simplify, and then you will have to come up with this final flow graph, and finally you can basically construct back the block diagram using this simplified signal flow graph. All right, so I think that's very much the end of lecture 2. I'll see you again in the next lecture.